Welcome back, everyone. Let's start chapter 10 today, which covers the rest of our carbonyl compounds, namely carboxylic acids, and then also all of the so-called carboxylic acid derivatives, meaning compounds that are related both by structure and by being able to interconvert one to the other to carboxylic acids. These types of compounds are exceedingly important, critically important in biochemistry. They show up everywhere in nature, and the reactions that are responsible for life as we understand life depend on this reactivity, particularly on the nucleophilic acyl substitution reactions that these compounds undergo, which we'll get to, I don't think in this video, but in the upcoming videos. But I'll say for now that these nucleophilic acyl substitution reactions are neither SN1 nor SN2. They go by a different mechanism. And so I think we're familiar with our functional groups, though if you need to go back and refresh your memory on that, right at the end of chapter 1, by all means do so. But carboxylic acids can be written RCO2H, so please be sure you know the structure of the carboxylic acid functional group. I'm mentioning nitriles here. They count as a carboxylic acid derivative, strangely enough. So remember, they're RC triple bond N, and they're one of these derivatives. And we'll talk briefly about all of these. All of these are going to get their jersey number called in this chapter, so to speak. What about the structure of carboxylic acids? Well, recall that the carbonyl carbon is sp2 hybridized, and what that means is that it and the other three atoms to which it's connected all lie in the same plane, are all coplanar. So that carbonyl carbon has trigonal planar geometry, or triangular planar, or planar triangular, or whatever your Gen Chem professor called it. But it's important to understand that that's a planar unit. And that's a pretty common feature of all carbonyl compounds, actually. Something which will become important later on when we talk about this feature in amide functional groups. And then when we do our last chapter together, which is on proteins and polypeptides, that's going to have a huge effect on the structure of proteins, and therefore why proteins, why enzymes, why all of these molecules do what they do. It's because of the shape that they take on. And that's directly influenced by this issue of this planar carbon atom. So we'll have more to say about that later. We talked in chapter 9 about ketones and aldehydes and how they undergo addition reactions, nucleophilic addition reactions to that carbonyl carbon. Carboxylic acids can undergo similar types of reactions, except that they're a good deal less reactive. And one of the things I'd like to do, though I don't think we're going to do it in this video, is give you an idea of the relative reactivity of all of these different types of carboxylic acid derivatives. It's something they bring up to an extent in the last section of the chapter. But I believe I can, at least I hope I can make that a little bit clearer still, and also present that a little closer to the beginning of the material so that you have some idea of their relative reactivity. But in terms of relative reactivity towards nucleophiles attacking this carbonyl carbon on carboxylic acids are lowest down. They have the least reactivity, the lowest reactivity. And that's largely because this carbonyl carbon contributes partly, along with two other contributing structures, to a resonance stabilized species in which the partial plus charge on the carbon atom, which is what makes it susceptible to nucleophilic attack in the first place, remember, is shared with both oxygens, actually, and certainly shared with this oxygen. So there's this other resonance contributor here. You find something similar, in fact, with esters, which we'll get to later on. So carboxylic acids are the least reactive of the class of compounds that includes them and all their derivatives. What else can we say about naming carboxylic acids and the structure of carboxylic acids? Well, I think I can leave you to learn about their naming pretty much on your own through OWL. And as usual, if you know how to name alkanes or alkyl halides or alcohols, you know 90 to 95% of what you need to know in order to name simple carboxylic acids. I will also point out, though I didn't mention it in the class notes, your book also covers the dicarboxylic acids, which are carbon chains of varying length but of a carboxylic acid functional group at both ends. And I don't know that I really care if you memorize their names. I'm not really too interested in your memorizing very many names, frankly. Though the simpler carboxylic acids, at least the smaller ones, maybe to some extent. We'll say more about that in a second. But the dicarboxylic acids show up a lot. The smallest is oxalic acid, which is just two carbons, and so it's two carboxylic acid functional groups connected to each other. And that's oxalic acid. That occurs in nature, and it's the reason why, for example, we can eat rhubarb stalks. So if you've had strawberry rhubarb pie, you understand all about that. But rhubarb leaves are toxic to us because they contain a great deal of oxalic acid, and so that causes kidney stones. So the reason I bring up the dicarboxylic acids is I did a general video on that, so one not meant for this class nor meant for my Chem 228 class, but for more of a general audience. Though what precipitated it was that I messed up in a discussion of the dicarboxylic acids for them. So if you're interested in learning a little bit more about the dicarboxylic acids, you can certainly do that. And not to sound as if I were a real YouTuber, but I'll put the link in the description below so you can check that out. Okay, so, but in terms of naming carboxylic acids, so the smallest ones mirror the alkanes, so the one carbon carboxylic acid can be called methanoic acid, methane methanoic acid. And likewise, the two carbon carboxylic acid can be called ethanoic acid, but people usually don't call them methanoic acid and ethanoic acid. So those names are not wrong. It's just that the names formic acid and acetic acid have been used for so much longer, and so people generally use those names for the first two carboxylic acids. But other things we can say about carboxylic acids, generally they smell quite nasty. And you're familiar with vinegar. Vinegar is an aqueous solution of maybe about 4 or 5% acetic acid. So just imagine what how strong the pure stuff must be. Carboxylic acids also are quite polar due to the presence of this very, very polar carboxylic acid functional group. And in fact, smaller carboxylic acids, 1, 2, 3, 4, 5 carbons maybe, tend to dimerize at room temperature. And that's done by hydrogen bonding. So if you need to review about hydrogen bonding in Chapter 2, please do so. What this means is that we get, for example, much higher boiling points for carboxylic acids than we would otherwise expect based on their molecular weight. And so, like I said, small to medium carboxylic acids will naturally do this. And again, the reason it matters about these hydrogen bonds is because we've got now to put in more energy in order to disrupt these hydrogen bonds and separate the molecules from one another, which is otherwise known as boiling. That's what we have to do in order to boil something. We've got to separate the molecules from each other. And since there's this extra attractive force that brings individual molecules of the carboxylic acids close to each other, that attractive force needs to be disrupted. And so that's why carboxylic acids, other things being equal, of significantly higher boiling points than compounds of similar molecular weight. And I would say this tends to be the case unless R is something really, really huge. If it's so big that the two molecules can't even approach one another, then this doesn't so much happen. What else can we say about carboxylic acids? Well, to no one's surprise, carboxylic acids are acidic. That might be the least profound thing I've said all week, but it's true. And just a reminder of how this works, one way of looking at acidity is by comparing acid dissociation constants, which is Ka, or more commonly we use pKa. And I'm sure you enjoyed endlessly drawing or writing out equilibrium equations like this, acid dissociation equilibria. This is one way to write it. You can also just write carboxylic acid only here, and on this side, the carboxylate ion plus H+. They mean the same thing. And so the form of the equilibrium constant looks the same. You can write either concentration of H3O plus ion or concentration of H plus ion. They mean the same thing. It doesn't matter which way you write it. Notice that in either case, even if you include water in the equilibrium equation, water falls out of the form of the equilibrium constant, right? Because we treat pure solids and pure liquids as though their concentration is 1. So that falls out of this equation. And you can look up Ka and pKa values. I certainly don't expect you to memorize any of them. I might have like 1 or 2 memorized, but it's not a thing that I devote my life to, and I certainly would never expect you guys to do that either. But the thing about Ka values in general, if you look any of them up, and I think you'll see them mentioned in the textbook or on OWL, the typical Ka values are some pain in the backside, like they tend to be like 5.63 times 10 to the minus 10th. And so they're just not real convenient to use. And that's why we use pKa values. We take minus the common logarithm or base 10 logarithm of these values. And then you get nice numbers like 5.63 or 9.11. It's just much easier to deal with. One thing to bear in mind is that as an acid gets stronger, or as we go to stronger and stronger acids, the value of Ka, the value of the acid dissociation constant, goes up, but the value of pKa goes down, right? So as you get to stronger and stronger acids, the pKa goes down. That's very important to remember. And that's thanks to this nasty little minus sign in front, which we kind of would have to do where they'd all be negative. So, but that's important to remember. Stronger acids have higher Ka values and lower pKa values. And the opposite's also true. Weaker acids will have lower Ka values and higher pKa values. So that's something worth bearing in mind. Why then are carboxylic acids so acidic? Well, there's a couple of reasons. One is explained by resonance, and one joke we often have in Chem 227 and 228 is if somebody asks you why something happens in organic chemistry, if you say resonance or the inductive effect, you're at least 75% likely to be right. And that's certainly the case here. This falls into that 75%. And so typical carboxylic acids of pKa values round and about 4. Anyway, between 2 and 5 is pretty typical for those. And the reason for that is that the conjugate base of the carboxylic acid, this carboxylate ion, is also resonance stabilized. And you got to remember what that means. It's not an equilibrium. It's not flipping back and forth between two things. There is one structure that is at all times a mixture of these two structures. Actually, if you really wanted to be picky, you can draw a third resonance form that is a plus charge in carbon and a minus charge on both oxygens. But as you can imagine, that one's going to be an exceedingly minor contributor. These two are by far the major contributors. The result is that the extra electron density on this oxygen atom is shared between the two oxygen atoms. It's spread out. And remember what a minus charge has to be by definition. It means there's extra electron density, all negative charge, or all electrons are negatively charged, and like charges repel. So the more we can spread out that minus charge, the more stable the species will be. And so that's why carboxylic acids are relatively eager to act as acids, to give up H plus and make the carboxylate ion and make the conjugate base. Because the resulting negative charge that you get is delocalized. It's spread out over a larger portion of the molecule. Compare that to alcohols. A typical primary alcohol might have a pKa rounded about 17, 18, somewhere in there. And so remember also with the pKa scale, again, thanks to that logarithm, remember the logarithmic scale means that every notch that you go on the pKa scale is a factor of 10. It's an order of magnitude. And so you could have a 14 order of magnitude difference in acidity here. And so that means that a carboxylic acid might be what is 10 to the 14th, like 100 trillion times more acidic than a similar alcohol. In fact, certain water or anything like that would certainly not be able to pull off the proton in an alcohol in any reasonable concentration. It requires much stronger bases, though certainly bases do exist that can do that for us. But if you look at the conjugate base of an alcohol, what we find is the conjugate base is not resonance stabilized as the conjugate base of a carboxylic acid is. Rather, the negative charge is localized on this oxygen atom. And so that one atom is to bear all of the extra electron density, all of that electron-electron repulsion. Now, oxygen's certainly not a terrible atom to do that. Oxygen's quite electronegative. And so that's why you would find that alcohols acting as acids or making oxygen bases like this is a good deal easier than doing the same thing on, let us say, a nitrogen atom or a carbon atom. So oxygen's certainly not the worst one, but how much better when you can delocalize the negative charge and spread it over more of the molecule. And that's why carboxylic acids are so much more acidic than similar alcohols, because these are otherwise a very fair comparison, aren't they? Same number of carbons, etc., as long as you keep the R groups the same. So that's an explanation of why carboxylic acids are so acidic. And an important principle, I've put it here in your class notes. In general, anything that stabilizes a conjugate base makes its conjugate acid stronger. There are no exceptions. And so in order to understand that, you need to have a very clear understanding of these terms, conjugate acid and conjugate base. Remember, they come together. They're always a pair. But you always have both one and the other. So in this case, the conjugate base of a carboxylic acid is a carboxylate ion. The conjugate acid of a carboxylate ion is the carboxylic acid. Or the conjugate base of an alcohol is this alkoxide ion, and the conjugate acid of this alkoxide ion is the corresponding alcohol. So they always go together like that. And anything you can do to stabilize the conjugate base, to make the conjugate base happier, will make the acid stronger. And resonance is just one effect. There are other effects, such as the inductive effect, that can also work to stabilize carboxylate ions. And we have here an interesting series. It's mentioned in your book, but I thought I'd look up the actual numbers for you. Of course, you don't have to memorize those numbers. Like I said, I had to look them up. But once we've looked them up, they make for a pretty interesting series. And so let's start with acetic acid, which is that's one I might have memorized. It's either 4.75 or 4.76 for the pKa, one of those two. So you can double check me on that. And what we're going to do is replace each of the three hydrogens on the methyl group in turn with chlorines. First one, then two, then three. So we're comparing acetic acid to chloroacetic acid, dichloroacetic acid, and trichloroacetic acid. And it's otherwise a very fair comparison. We're very much comparing apples to apples and really isolating the effect of adding additional electronegative chlorine atoms. And what I think you'll see is that the pKa goes down little by little. When we change one hydrogen to a chlorine, we go from 4.75 to 2.86. That's almost 2 orders of magnitude. So this acid is almost 100 times stronger than acetic acid. This one, somewhere between 10 and 100 times stronger still. And then trichloroacetic acid, a similar amount stronger still. pKa is way down at 0.66. By the way, since I know some of you will be wondering, can pKa values be negative? Absolutely they can. That happens sometimes. You're talking crazy strong acids here, though. But be that as it may, in order to understand this, you need to be able to consider what the conjugate base of each of these looks like. So remember, we're going from the carboxylic acid to the carboxylate ion. So you need to be able to imagine changing the OH to O- in each of these cases, right? So you have negatively charged species for the conjugate bases of all of these. But as we replace hydrogen atoms with electronegative chlorine atoms, remember what it means for an atom to be electronegative. It's sucking electron density in bonds toward itself. And so the more chlorines we load up here, the more electron density those chlorine atoms can pull toward themselves away from the oxygen with the minus charge, which is the conjugate base, the respective conjugate base of all of these species. And so it's really a similar effect to, or I shouldn't, it's not at all similar to resonance. It's not at all resonance. But the effect is similar to that of resonance in that it's spreading out the minus charge in the conjugate bases, in the carboxylate ions. And so that makes, as you change hydrogens to chlorines, that makes the corresponding acids, which we see here, stronger and stronger. And that's just one example of a structural effect on acidity. It's a pretty common, it's pretty commonly seen. So like I said, memorizing the numbers here is not important. But understanding the trend and why the trend is what we see, I think, is important. One last point I want to make in this video, which is something we know already, is that being acidic, carboxylic acids can be deprotonated with even a moderate base. And in chapter 15, we talked about using sodium hydroxide or potassium hydroxide to make soaps. But you don't even need to go that far. You can use a much more moderate base than that. Even something like sodium bicarbonate, NaHCO3, which is baking soda, is a strong enough base to deprotonate a carboxylic acid. If you've ever mixed vinegar and baking soda, then you know that to be true. I've left out the sodium here. Instead of writing NaHCO3, I wrote HCO3-. I just drew the anion, because the sodium's only a spectator ion. It doesn't do anything here. You could put it in there. You could write NaHCO3. You just need to add Na+ on this side if you want to balance the equation. But I think it's a little easier to see without, since again, the sodium ion doesn't do anything. But the bicarbonate ion is not a very strong base. I think carbonic acid is a pKa rounded about 9 or 10, somewhere in there. But whatever the case, this base will pull off the proton from the carboxylic acid and make H2CO3, carbonic acid. Carbonic acid is pretty unstable and it breaks up pretty quickly into water and carbon dioxide. And that's the bubbles that you saw when you mixed the two. It was the carbonic acid decomposing and making water and carbon dioxide, and then the carbon dioxide bubbles out of the solution. That's also the explanation of the bubbles in your soda, right? It's because there's carbonic acid there. And so that's why your soda will go flat if you leave it out, right? Because all the CO2 will go away. So this is just a reminder that the acidity of carboxylic acids means they will react with bases, and they don't even have to be particularly strong bases. Hydroxide ion will certainly work, but you don't even need to go that far. Good, so I think that's a good place for us to stop for right now. We'll continue on in chapter 10 in the next video. So until then, have a good day.